So now let's see briefly why the consensus-based total order broadcast algorithm that we considered is correct. So an important observation appears in the first bullet here, and what it says is that the way the rounds are being set up by the algorithm actually ensures that a process never switches to the next round before it is completely done with the current one. And by completely done, I mean that all the messages that have been decided in the current round are delivered. Okay, and that implies that the message, once delivered, it can't be proposed again. So once it is delivered, it is removed from the unordered set. And since only after that point that it is delivered, a new round of consensus can be activated, that message won't be included in the proposal of that round and won't be proposed or delivered again. Okay, so this is what's being said here. So the message cannot be proposed in any later round. And that means that for every process and for any given message, there is only one round in which that process can potentially deliver that message. And since we also have agreement property of consensus, this round is also unique everywhere. So that means that if a process P delivers message in round R, then any other process Q that delivers the same message also delivers this message in the same round R. So this claim here is going to be useful for proving total order. And this is what we are going to do in the next slide. So we are not going to discuss how to prove the remaining properties, but you should make sure that you know how to do this. So it's your self-study. And of course, you can find more details in the textbook. So given this claim that messages are delivered in unique rounds by all processes, let's see how we can now prove total order property. So suppose we have two processes, P and Q, and both deliver messages M1 and M2. And in addition, we also know that P delivers M1 before M2. Okay, so this is the premise of the total order property. Okay, so we have two cases to consider. So case one is that both messages M1 and M2 are delivered in the same round. And case two is that they delivered in different rounds. Okay. So let's first consider case one. So in case one, since we know that all messages are delivered in unique rounds by claim one, and we know that Q delivers both M1 and M2, it must deliver them in the same round as the one at which P delivers M1 and M2, and this is round R. Okay, and since we know that all messages that are delivered in the same round are deterministically ordered, right? So this is by the algorithm, because we apply this deterministic sort function that we have seen in the pseudocode, means that Q will also deliver M1 before M2. Okay, so this completes the first case one. Now let's see what happens in case two. So here we have that P delivers M1 in round R1 and M2 in round R2, and those are different rounds, and we can assume without loss of generality that R2 is greater than R1. Okay, so again, by the uniqueness of the delivery round at all processes, since we know that Q delivers both M1 and M2, it must deliver M1 in round 1 and M2 in round 2. But we also know that R2 is greater than R1. And by the way algorithm operates, and we discussed that in the previous slide, a process won't proceed to a later round before it's completely finished. It means that delivered all the messages that have been decided in the current round. Okay, and therefore Q will first finish with all messages delivered in round 1, and therefore it will deliver M1, and only after that it will proceed to further rounds, and finally we'll get to round R2. In that round it will deliver M2. Okay, so that means that Q delivers M2 after M1, and this is exactly what we need, and this completes the proof of the second case. Okay. So what are the limitations of this algorithm? So first, as we have discussed, it is critical for correctness that processes synchronize on rounds. And that means that they can't switch to the next round before decision is reached in the current one. And that negatively affects the algorithm's performance, both message throughput, that is the number of messages delivered per time unit, and the latency. Okay. So, and the reason that happens is that while a specific consensus instance is in progress, new messages keep arriving and they enter the unordered set. But these messages remain stuck in the unordered set until the current round of consensus reaches decision. And that, of course, can take time. So depending on the algorithm that is being used to implement consensus, that can take several message delays. Okay, so that time is basically unused for ordering new messages, and that leads to the performance problems. So practical algorithms actually address this problem, and they allow ordering of multiple message batches to proceed concurrently. However, this requires much more complex implementation of total order than the one that we considered. So in particular, it needs to expose some of the inner workings of the consensus algorithm, such as the current leader. Okay. So these algorithms, they still use a consensus as building block, but the separation between abstractions is not as clean as it is in the case of the algorithm that we discussed. So the examples of such implementations, if you are interested to explore on your own, are as follows. So they include the original Paxos paper, so not the Paxos Made Simple paper that we followed in our presentation of Paxos, but the paper where Paxos was originally published by Leslie Lamport. So there is a complete implementation of state machine replication based on Paxos consensus that we considered. So this is a theoretical paper, but then there are a number of practical implementations that followed similar guidelines. So that includes Apache Zookeeper, Raft, etcd, libpaxos, and many others as well. Okay, so we have reached conclusions. So in this lecture we discussed total order, also known as atomic broadcast. We considered, we defined and gave implementations for both non-uniform and uniform variants of this abstraction. And we argue that this abstraction is very important, in particular because it facilitates replication of generic services. And to do that, we apply the state machine replication design pattern or paradigm. And this paradigm basically models a service as a deterministic state machine, and then it replicates the resulting state machine, and then the consistency of this state and of the outputs of this state machine is achieved thanks to the total order that is used to disseminate commands. So we said that total order broadcast is equivalent to consensus, and for that reason it can't be implemented in a fail-silent model. So fail-silent is a completely asynchronous model without any timing assumptions or failure detectors. We have seen that total order broadcast can be implemented using consensus as a black box. So we developed an algorithm for that and proved that it is correct. And this is the approach that is most often followed in practice, even though practical implementations are more efficient than the one that we considered, but that requires more complex algorithms which employ cross-layer optimizations. So the algorithm implementing total order broadcast needs to know some information about how the underlying consensus is implemented. This completes this lecture, and in the next lecture we'll be discussing this exciting topic of Byzantine fault tolerance. Thanks for listening, and see you in the next class.